Welcome back, engineers. In this video, we're going to talk about something really exciting, magnets. You probably already know that magnets can stick to certain metals, like the fridge at home, but magnets can do much more than just hold up pictures. Here's your challenge to start today's lesson. Take the motor from your kit and connect the two-color LED to the bottom of it. Spin the motor shaft as fast as you can. What do you notice? What happens if you spin it the other direction? Well, if you were able to spin it fast enough, you were probably able to see the LED light up. But how's this possible without a battery? What you've done is discovered one of the coolest connections in science. Electricity and magnetism are linked. By the end of this video, you'll be able to explain what a magnetic field is. You'll be able to demonstrate the relationship between electricity and magnetism. And you'll be able to explain Faraday's law and why it's important to electrical engineers. What is a magnet? Well, let's start simple. A magnet is any material that creates a magnetic field. Cool, but what does that mean? A magnetic field is an invisible area of force around a magnet. You can't see it, but you can observe it when a magnet attracts or repels objects. This field is created by something called electron spin. Inside every atom, electrons are spinning. That spinning creates a magnetic field with a north and south pole, just like Earth. Usually, the spins are just random directions and they all basically cancel each other out. But in some materials, like iron, the electron spins can line up in the same direction. When that happens, their magnetic fields get added together and the material becomes magnetic. When an object is magnetic, the field creates a north and south pole on opposite sides of the object. Place a north pole near the south pole of a different magnet, and the two fields will pull the two magnets together. But if you turn one around and you've got two north poles facing each other, they're going to push each other away. The same thing happens with two south poles. They're also going to push each other away. At the beginning of our unit, we talked about electricity and how electric current is just the movement of all of those electrons in the same direction. When there's electric current going through a wire, it creates a small magnetic field around the wire. It was first discovered by a Dutch chemist and physicist who publishes experiments using a compass needle with nearby electrical currents. These magnetic fields are pretty weak, though, and not very useful by themselves. Just like the electron spin inside a magnet, though, if we line the fields up together, we can amplify their magnetic properties and make it stronger. We can build a crude electromagnet using the SparkBlocks battery, about 5 feet of 22 gauge solid core wire, and a steel rod. I'm going to very neatly wrap this wire around the rod and then plug it in. The pins are on the back of the battery for connecting to breadboards, and they accept a 22 gauge pin, so this wire is the perfect size. When I connect this to a battery, the wire generates circular magnetic fields. The fields rotate the electrons inside the steel rod, lining them all up. They're no longer canceling each other out, but instead combining their power together. Using this electromagnet, I can pull this floating pin along without even touching it. When I disconnect the battery, though, the magnetic field disappears and I can't pull the pin anymore. What do you think will happen if I wrap the wire more times around the nail? Will the electromagnet get stronger, weaker, or will it stay the same? Let's go ahead and try it out. I'm going to double the number of times that wire's wrapped around and see what it does. Wow, that's way stronger. I can even pick the pin up out of the water or grab them from the container. Now let's go back to your motor activity we did at the beginning of this lesson. When you spun the motor, it powered the LED. That's because a moving magnet can also create electricity. This idea is called Faraday's law. It says that when a magnetic field changes near a coil, it makes electricity flow. That's exactly what's happening inside your motor. There's small magnets inside that are moving past coils of wire. So let's get that motor and dual LED back out. In the beginning of this lesson, we spun the motor in both directions. One way gave us a red light, and the other one, a blue one. Go ahead and give it a try again. This is because the direction the magnet is moving determines the direction the current is flowing. Unlike a battery where we have a positive and negative side, we create the positive and negative by pushing electrons to one side or the other. What we've created here is a generator. Generators, not too different from this, are used to convert rotational kinetic energy into electric energy. They're used in dams, windmills, and nuclear power plants. And just like that, we've connected electron spin, coils, and current into one big idea: electromagnetism. The discovery of electromagnetism is one of the most important in the development of our technology. Without it, we wouldn't have motors, power generation, wireless power transfer, or many of the electrical components we use in our electronics. Way to go! Let's review what we learned today. We learned what a magnetic field is and how it's created at the atomic level. We demonstrated the relationship between electricity and magnetism by creating electromagnets. And we learned that Faraday's law explains how power can be generated by using magnets and coils.